Question number 3. An IGCSE student is investigating the relationship between the extension of a spring of unstretched length and the load hung on the spring. The apparatus is shown in figure 3.1 below. The spring is shown larger than its actual size. 3a. The data collected by the student are presented in figure 3.2. 3ai. Consider the readings that the students should take and write appropriate column headings with units in figure 3.2. To investigate the relationship between the extension of a spring and the load hung on the spring, there are only two readings need to be taken by the student. The readings are load or weight in Newton and length in millimeter. Why in millimeter? It is because the third column, this one, the extension, already used the unit of millimeter. Then the length must also be in millimeter. Question 3a Complete the third column in the table by calculating the extension of the spring. To fill in the extension column, we have to subtract each length with the initial length. The initial length is the length of the spring when the load is equal to 0. Therefore, the initial length of the spring is 25 mm. Now let's fill in the extension of the spring one by one. The first row, this is 0. Why? Because 25 minus 25 is 0. Second row is 30 minus 25, which is 5 mm. The third row, 35.5 minus 25. We will get 10.5 mm. The fourth row is 40.5 minus 25, which is 15.5 mm. The last one is 46 minus 25, which equal to 21 mm. Question 3a, III. State the unstretched length of the spring. The unstretched length equals to the initial length. The initial length here is the 25 mm. Therefore, the unstretched length is also 25 mm. Question 3a, IV. On figure 3.3, plot the load and extension data from the table. Draw a line of best fit for the graph. Let's check which data we have to plot on the graph. This is the load and this is the extension. So we will use column 1 and column 3 for the data of our graph. First, we have to label the x and the y-axis. You can choose which one to be the x-axis and which one to be the y-axis. In this drawing, I will show you how to do both. In the first drawing, the x-axis is the load, while the y-axis is the extension. Don't forget to put unit on the label. The extension unit is millimeter, the load unit is Newton. Then, write down the values of the scale. You have to choose the scale for your graph carefully. Make sure your graph can fit in the space provided Also, your graph must not be too small. At least 3/4 of the space provided must be covered by the line of your graph. This skill will be developed along with your study in DCP program. This is the 0, and then 5.0, 10.0, 15, 20, and 25. So you can see on the y-axis, I choose the scale division of 5 mm for each 10 small blocks. For the x-axis, 0.1, 0.2, 0.3, 0.4. So every 0.1 Newton, there will be 10 small blocks. After the values filled in, plot the data on the graph paper. The data are 0 with 0, 0.1 with 5.0, 0.2 with 10.5, 0.3 with 15.5, and 0.4 with 21. After all the data plotted correctly, draw a line of best fit for the graph. Drawing a line of best fit is also a skill that will be developed along your study in DCP program. But now, the meaning of drawing the line of best fit for you is trying to draw a line which passes through as many crosses as possible. Like this one. Our first type of graph is done. Before we move on to the second type of graph, I will show you how to calculate the spring constant for this graph. So, we will answer question number 3AV before drawing the second graph. This is done to avoid the mixed up of working, because the working for question number 3AV depends on the choosing of the axis. The working is different for the first and the second type of graph. The spring constant equals to load over extension. So, for the first graph, the spring constant equals to run over rise, because the load is on the x-axis and the extension is on the y-axis. Once again, spring constant equals to load over extension. So for this type of graph, the spring constant equals to run over rise. Draw a right angle triangle on the graph to mark which 2 points are used to calculate the spring constant. I choose 0.3, 15.5, and 0, 0. So, my right angle triangle looks like this. The run over rise equal to 0.3 over 15.5. So, the spring constant equals to 0.3 over 15.5 or 0.019 Newton per millimeter or 0.19 Newton per centimeter. That's the value of K. Now, let's draw the second type of graph. In the second drawing, the x-axis is the extension in millimeter, while y-axis is the load in Newton. Once again, don't forget to put unit on the label. Then write down the values of the scale. I want to remind you that you have to choose the scale for your graph carefully. Don't make it too small, but also it has to fit in the space provided. At least 3/4 of the space provided must be covered by the line of your graph. I choose the same scale as before. For the extension, I divide it into every 5 mm. As for the load, I divide it into 0.1 Newton. After the values filled in, plot the data on the graph paper. 0 with 0, 5.0 with 0.1, 10.5 with 0.2, 15.5 with 0.3, 21 with 0.4. After all the data plotted correctly, draw a line of best fit for the graph. Try to draw a line which passes through as many crosses as possible, like this one. Our second type of graph is done. Let's calculate the spring constant for this graph. In the first graph, the spring constant equals to load over extension or run over rise. In the second graph, the spring constant still equals to load over extension. But because now the load is on the y-axis while the extension is on the x-axis, then the spring constant now equals to rise over run. Once again, spring constant equals to load over extension. The load now is on the y-axis. The extension is on the x-axis. So, the spring constant now equals to rise over run. So, be careful. Draw a right angle triangle on the graph to mark which 2 points are used to calculate the spring constant. I choose the same points, 15.5 with 0.3, this one, and 0 with 0. So, my right angle will look like this. The rise over run equals to 0.3 over 15.5. Then the spring constant equals to 0.3 over 15.5 or 0.019 Newton per millimeter or 0.19 Newton per centimeter. That's the value of our spring constant or K. The results of the two different working are the same and must be the same. Then our calculation is correct. In the test, you only need to draw one type of the graph. So, choose which one you prefer to draw. Question 3b. The student decides to repeat the experiment using a spring made of a different metal in order to study how the extension may be affected by the metal from which the spring is made. To make a fair comparison, other variables must be kept constant. Suggest 3 variables that the student should keep constant. The first one is the initial length of the spring. Second variable, the amount of load added each time to the spring. The third one, the diameter of the wire used to make the spring. Those are the three variables that the student should keep constant.